Hello everybody, welcome back to the second session of our Ray Tracer challenge implementation in Rust, while I'm learning Rust and playing around here and getting to know all these things, while I am doing the chapters from this book, the Ray Tracer challenge. Hello, just a short intermission from a little bit wiser and older Jacob, which by now has done some of those recording sessions and some more streams, and has realized he forgot to tell you that there are information in the description below regarding the GitHub repository where you can get all the code we are writing here to follow essentially along. Furthermore, please bear with me while I'm still learning on how to present all the different things I'm doing currently during the recordings. I get better from recording to recording, from session to session, so please be a little bit patient. And now, back to the program. Have fun. We last stopped in the middle of chapter 1, actually, while it was going quite slow, and we figured out just some things about Rust, which we are going to continue now in this session. So let me just take a look what we've done here the last time, because it's a couple of days since we stopped. But I guess we had this tuple struct, yeah, I remember it, which either holds a point or a vector, and we just implemented adding two vectors or two structs of this type, the tuple. We just implemented on how to add two tuples together. Yeah, and I guess we wrote some tests. Yeah, I see. Okay, so let's make sure that I haven't changed anything and make it break in the meantime. No. Okay, still working, so yeah, I guess we can just follow up with the next part of the implementation, which according to the book should be, let me take a look, actually the next one would be to subtract two tuples. So it's the following test we should write, and we will, I guess, write it. Point says it is a tuple, tuples are added up. Okay, so the next one would be a function called fn tuples are subtracted. Let's do this. So let tuple 1 equal tuple. And this is actually something I've been thinking about. I know that we can instantiate a tuple like this direct instantiation syntax used within Rust with these curly braces. But instantiating a vector or a point, we have this convenience functions we created, which are simply called vector and point. And I guess I would actually like to have something as well for a tuple, so I guess I've written up a little bit on it, and I guess it is a best practice. I'm not 100% sure, but I would like to have this actually. So let's just implement this here, ZF64, yes. And W is a floating point as well. I just can't get used to this typings actually. So yeah, we are doing self here, and so we are doing self X, Y, Z, W here, I guess. Should work out like that. Why can't I format this? Maybe because I've just kind of botched up the things around here. So yeah, now it's formatting again. Makes me wonder if we should change this to a function call actually, to now call there the new function, but I guess that's not really needed. So let's just change up things here a little bit and have this one do it like this and use this nice new method here, which is actually not working as I expected. Help use expect value found struct tuple. I think there is a colon missing. Yeah. So now it's working. Yeah, I kind of think I like this better. Maybe. I'm not 100% sure. But now at least it's the same for every invocation, the same style, I guess, and I like that kind of better. Let's just chain these together here, and let's do it this way and delete that. And now we need to delete the naming here. And now we are doing the same thing here. Just like that. That has to be gone, that has to be gone, and that has to be gone there. And now let's do the same thing here as well. Yeah, I kind of like this better, definitely, because I can now better read this actually without the X, Y, Z things in between. So yeah, I guess I like that. So function never used is completely okay. Let's just check if all our tests are still running. And now we have all the tests running, but we might have a warning. Yeah, that the function is not defined. Perfect. But I guess we have now refactored it nicely. So now let's write our test that tuples are subtracted actually. Let's do it really test driven. We have 2 points, so let's use that. It's using 2 points for the first subtraction test. It's a point 3.0, 2.0 and 1.0. And let's call this point 1, and let's call this point 2, and the second point is 5.0, 6.0, 7.0. So let's implement this one, and the expected is actually a vector, which does absolute make sense, because if we subtract 2 points from each other, we get a vector in the direction of those two, the line connecting those 2 points. So it's an expected vector is now tuple vector, and it should be -2, -4, and -6. Let's assert equality here, and let's say that we are assuming that point 1 minus, come on, point 2 equals expected vector. Now let's format this. Yeah, cannot subtract. That is exactly what I would expect if I now run this. Yeah, cannot expect it because we haven't implemented it yet. Okay, we haven't even defined a test here yet, but okay, it's not. It doesn't need to run the test to encounter the error that it hasn't a subtraction not yet implemented. But I guess subtraction is working more or less the same by implementing this operations trait for it, I guess. So let's do an operations sub, I guess. The result will be no, it's if subtraction from this one from the tuple from itself will be an output of self, because we are outputting a tuple again. And then I guess Fn sub, maybe? Missing sub in sub implementation. Yeah, I guess that makes absolute sense. So we are getting self here, and we are getting some other here, which is a self, and we are returning self. So what we need to do here now is we want to return a new tuple, which is actually self.x minus other. Come on, other.x self.y minus other.y self.z minus other.z self.w minus other.w. So no, we don't want a semicolon there. I've learned that. So let's format that so that it looks nicer. And now let's run our tests. They're actually passing, so we've just implemented subtraction, at least for 2 points. But no, we've not really completed this test because we need to make sure that expected vector is a vector indeed. No, we no. That's not okay. Let's do it other. Let's actual. This is the expected result now, and this is the actual result, and the actual result will be 0.1 minus 0.2, and we are now having here actual result is compared with expected result. Yeah, that's a lot better. And now we will check that actually the result is a vector as well. Result. Didn't I change that just a second ago? Okay, I don't know. Maybe I've just triggered the wrong shortcut. So actually this does implicitly check this. Maybe we won't do it this way. This of course does implicitly check this because we are checking the W component of the result, and it has to be obviously the same. Otherwise this check would fail. But I like to check this explicitly actually. So let's run the tests again. They are still passing. So because the next test of course is what happens if we are subtracting a vector from a point. So this function actually should be called point subtraction. No, let's call it subtraction of points result in vector. So now the next test would be Fn subtraction of subtracting a vector from a point. Subtracting a vector from points. Let's just call it that. Maybe I should start naming the tests as they are named in the book for better reference. I think I will try and go with that for now. Let's check how this works out. So yeah, this is a test, and what is it that we need here? I think I will start maybe even trying to name things like they are named in the book, in the pseudocode of the book. I'm not sure. Let's just try it and we will see how we like it, or better said, how I like it. So this one actually should be a point. So let's do this. We have a point here, and this point is actually a 3.0, 2.0, 1.0. And we have a vector, which is a vector, of course, then. What's just happened there? It auto-completed it. 5.0, 6.0, 7.0, whoa, no, 7.0, something like that. And then we have expected result equals tuple. And this now, of course, has to be a point, because we are simply moving from the given point by the given vector, and we get a new point. Makes sense. So this should again be 2.0, minus 4.0, and minus 6.0. But this time as a point. So let's again assert that we should actually calculate the result. So let actual result be the point minus the vector. And now we are asserting that actual result is a point. Come on. So, and we are asserting that actual result assert equality actually is equal to the expected result. So let's test this as well. Okay, passed. Nice one. So what is on the next test we are about to write here? Of course, what's happening if we subtract two vectors? If we're abstracting the directionals of two vectors, like we have one, for example, we have one here and we have one which goes this way, then we actually want the vector which goes from this point to that point. So it should be a vector as well. So let's name this function subtracting two vectors. Subtracting two vectors. And this is a test function as well. So let's do that. Let v1 a tuple, which is a vector. Is it actually is it using 3, 2, 1, 5, 6, 7? I'm a little bit, let's just reuse that so I don't have to put in all this data again. So this is vector 1 and this is vector 2, and now we have expected result again, which in this case is a vector, and we have the actual result, which is v1 minus v2. And then we have our two assertions, but now this needs to be a vector. Nevertheless, the operation should still be the same. Okay, something is wrong there. Expected item. What have I done wrong there? The hash sign should be outside of these square brackets. Okay, that works nicely. Okay, so we have actually finally finished implementing subtraction. Not that a great thing, but we did it and we wrote all the tests and it's working like it should. So now we are taking a look at negating tuples. So the next thing we should do is implement negation. Can we actually? That's something I don't know. Now we have to take a look at the what would it be? Rust std ops or Rust ops negation. Is there something like, can we override something like negation? Trade std ops neg. Is it what I think it is? Let's just check. The use of minus to negate its value. Okay, so Yeah, okay. This actually, we can actually override negation. That's kind of nice, actually. And I'm just seeing here that this might be a good idea to simply use this in the function signature itself when we define it here anyways. Yeah, I like that as well. So let's do two things. First of all, let's change this here. Oh, I've called it right-hand side here. And I've called it other here. I guess I like other better. So let's, is there no refactoring for this here? Rename? Why isn't there, why isn't my shortcut for renaming not working? What the heck? Let's rename this one at least. But wait a second. Why isn't it, I can't, that's strange. Okay, that's kind of, why isn't, somehow my renaming shortcut, which is actually displayed here, Shift F6 is not working. Need to take a look at this sometime, but not now. So now we should change this one to, if I get it, if I've seen it correct, how do they do this? Self output. So why actually self output? But that doesn't make any sense. Why is this actually working? But I could do output, I guess. Cannot find type output in this scope. You might have want to use associated times self output. But why? Okay, in this case, let's. Why is this self output? Because self is obviously the type. Because we've defined then the type output on this trait, which now belongs to this type, and so, holy crap, that's kind of recursive typed. Whoa. But yeah, I guess this is the way to do it. I'm not 100% sure I like that. Let's check. Okay, our tests are still running, so we have not destroyed everything. So now let's implement ops, and we have just learned there is a ops neg. I guess I need to define self here as output for the template as well for tuple. So we have now type, well, no, I don't guess this one hasn't. That wouldn't make sense because it does not interact with anything. So output would be self again. And now we should implement the neg function, which should actually get self and should return self output as we have just learned. Yeah, we haven't implemented this now. And negating a tuple, a vector or a point, is actually in case only the negation of all its components. So we should just return a new tuple here, which actually would be -1 multiplied with, or essentially it would just be minus self x minus self y minus self z minus self w. So no. So yeah. But I did it again. I implemented it again and before writing the tests essentially. Okay, so let's start writing a test for this. The first test is actually, here is subtracting a vector from the zero vector. The zero vector, nice. So, oh no, that's actually a subtraction test. Subtracting a vector from the 0 vector. That's essentially the book's way of explaining what the negation of a tuple is, or of a vector, better said then. So we are actually copying this, I guess, because why not? But now the first one is called, it is called 0. Let's call it 0, and it is simply a vector where all its components are 0. So now our expectation would be, of course, that this one is just the negation of the first one. So this is 0 minus this one, and this should actually run fine. Let's check. It runs fine. Great. So what's the next test we are about to implement here? Because now we are implementing the negating a tuple, actually. So yeah, so let's just the test is just called negating a tuple. I actually like going with the naming of the book. Maybe I will go ahead and adapt the rest of it. We are not that far in, I can do that. So they are calling it A, and A is simply a tuple new, which is 1.0 minus 2.0, 3.0 minus 4.0. Yeah, that's actually everything there is to it. And now we are going ahead and having let expected result would of course be a tuple, which is then minus 1.0, 2.0, minus 3.0, 4.0. So the negation of it. And we have let actual result is minus A. And now we expect, no, not expect, assert. First of all, no, we simply assert equality between actual result and expected result. And this should actually, why is it removing this? That's kind of strange there. It is kind of removing my, what the hell? Is it doing it because I have, okay, I see. So yeah, let's do it like this. So now we should be able to run this, and it should work. Yeah, nice. So the next thing in the book actually is scalar multiplication and division. So essentially multiplying a tuple by a scalar value, a vector or a point. A vector especially because essentially we have point vectors, but I'm not thinking about this, works the same way. So it's every component is simply multiplied with the scalar value. So let's now do this here by first writing the test this time. Multiplying a tuple by a vector. Multiplying a tuple by a vector. So multiplying a tuple by a vector? Never ever. Multiplying a tuple by a scalar? Yeah, multiplying a tuple by a vector, like cross product or something like that. I guess we will do that later. So yeah, how is it called? We have a tuple which is called A again. So it's tuple new, and it's what it is here, 1 minus 2, 3 minus 4, that's actually exactly the same tuple. Let's reuse it to save me some typing there. And what are we doing with it? We are multiplying it with a scalar value of 3.5. So let's call this one scalar, and it's, or let's call it multiplier. Let's call it multiplier 3.5. And I guess the system can make out which value it is. I'm not 100% sure here because it might automatically create a let multiply. Is it like this? I guess it is like this. Yeah. Let's make sure it is making a 64-bit floating point of this, like in our struct where we always use 64-bit floating points. So yeah, I guess then we need the expected result, which should be tuple new, which should be, it's too late for me to calculate this now. It's 3.5, that's of course, okay, the next one is 7, that's easy. No, it's actually -7, and this one would be 10.5, and 4 times it would be minus 4 times is -14. So yeah, if I hopefully correct this right, that actual result is A multiplied with the multiplier. So assert equals actual result is expected result. So now it's failing to compile because, yeah, there is no multiplication implemented. Right, we haven't done that yet because now we are doing test first. And I'm simply guessing that I can do it this way. There might be something like ops mul or mult. Mul seems good for me, so let's implement this one for the tuple, like the type, of course, is again the output is self, and it's a multiplication in this case with a scalar floating point value actually. So we need to implement this, and the mul operation, which gets self, I guess, and should we call it other here, or should we call it then? We should call it other, I guess, which is an F64. Do I need to actually specify this here? I don't think so, because this trait does already this one, and this is self output. So yeah, what's actually, no, okay, I guess it needs this here. Okay, we need to define this. Have we done it before as well? Indeed, we need to define the typing. That makes absolute sense. So yeah, okay, so let's just output a tuple here again, which is then self.x multiplied with other, self.y multiplied with other, self.z multiplied with other, and self.w multiplied with, you guessed it, come on, other. So let's do this, and let's check. What did I do there? That's definitely the wrong command. So yeah, our test is passing. Nice, we've implemented at least multiplication for this first test, but now we are going to implement here now a second test, which is specified here for multiplying a tuple by a fraction. So let's do this. Fn multiplying a tuple by a fraction. So I guess this is using the same data set again. Yeah, it is. So let's kind of copy all this here because I don't want to type it again. The multiplier in this case is now 0.5, and of course this changes the result. We have now here, undo that, what have I done there? We have now 0.5 here, a minus 1.0 here, 1.5 here, and a minus 2 here. So let's save this and let's check. And yeah, it's passing. Nice one. Essentially, now we need to implement the division with a scalar next, because that's essentially what we have done here. But the book says we should implement the division operation if it is possible to do that. So let's do that, because we need that later on. So let's write the test. It's called dividing a tuple by a scalar. Dividing a tuple by a scalar. Yeah, nice. So let's do this. It's again actually mostly the same, so let's copy this to make things easier for us. So we have this, and now this is the divider. Is it the divider or the divisor? I'm never really sure about this, so let's quickly check this. Divider. I wanted divide. Divisor definition math. Divisor, a number by which another number is to be divided. A number that divides into another without a remainder, the greatest common divisor. What the hell? A number by which another number is divided. Wait a second. Yeah, it's the divisor. So yeah, it's kind of hard to understand if you're not a native speaker, an English native speaker. So this is the divisor, actually. And now what we are doing here is using this divisor. The divisor is, I guess, 2 here now. Yeah, makes absolute sense. So the result should be the same, but of course this will not compile now because we have no implemented stdops division. I really, by the way, like the compiler output of Rust, because it is like, okay, here, maybe I can't divide that, but hey, take a look here at this trait. I know it exists and it overrides this operation. Maybe you forgot to implement it. That's really nice. That's really good. So let's implement this one. Let's scroll down here a little. It's then ops. Was it div? It was div with an 64-bit floating point, and we want to implement this trait for tuple. Yeah, we want to, and we have type output is self again, and now we have here most likely the div part, which gets self and gets other, which is a floating point 64, and it returns self output. So let's do this. We are actually returning a new tuple here, which new is written in lowercase. So which is self x divided by other, which is self y. Come on. Divided by other, which is self z divided by other, and which is self w divided by other. So no semicolon at the end. What is it? Celt. So of course it can't resolve celt. I get that because we wanted self. So let's now format this file. Let's save it. Let's run the tests. Tests are running. Yay! We now have implemented dividing. Is there any other Yeah, okay. The next implementation would be magnitude, to calculate the magnitude of a vector. Are we actually implementing it on anything else than vectors here? I don't guess so, because it is always checked and tested on a vector. So yeah, magnitude. What's magnitude? Magnitude actually, magnitude of a vector is actually the, how can I describe that? Essentially the length. A magnitude is essentially the length of a vector. So if we would be going from one end to the vector to the other end of the vector, we would be going this distance, this calculated distance. So now let's implement the tests as the book says we should. There is the first one is computing the magnitude of vector 1, 0, 0. So yeah, let's do this. Compute the magnitude of vector 1, 0, 0. Yeah, so I guess we need the vector then. Let v tuple vector 1, 0, 0. And now we want this, let expected result, the magnitude of the vector 1, 0, 0, of course, as we are only moving in the x direction in 1, would be 1. That's kind of expected there. So I guess we will simply implement a function called magnitude on this struct. So yeah, let's do this. Actual result equals vector magnitude. And then we have assert. Come on, assert equals that actual result is expected result. So yeah, let's run the tests, but of course they won't run because, yeah, method not found in tuple. Makes absolute sense because we have not implemented it yet. So let's get going on this one. Where's our tuple? There's our tuple implementation. So let's add a new implementation here. Can we actually, I like this one because this is all the creation stuff. Can we actually have another impl section for tuple? Is this working in Rust? Let's take a look at this. Can I do something like impl tuple here again? And at least it doesn't cry out loud. Let's take a look. What have I said I wanted to implement? Magnitude. Magnitude. So, self, is this self now, or is it, I guess this is a reference to self, maybe? And it is returning a scalar value because the magnitude is scalar. So mismatch type, expected F64 found. Yeah, because we haven't returned something yet. So magnitude is this, was it borrowing or reference? Or I'm not 100% sure what I'm doing here with this referencing stuff yet in Rust. But let's just take a look at how it works. So if this works, it would be nice. So essentially, to compute a magnitude of a vector, we are using the theorem of Pythagoras. Pythagorean theorem? Yeah, there's the one with the hypothesis. I don't know the English terms for this mathematical stuff. I'm sorry. I could search for that, but actually it is this thing in a triangle where we take the both sides which are directly which are adjacent to the 90-degree angle, and we can, by squaring them up and getting the square root, adding them and then getting the square root of them, we can get actually the length of the other path. It's Hypotenuse and Kathete in German, but I could look it up. I don't know. So we are actually using this one, and for this to actually work out for us, I need to take a look at how to use math functions in Rust, because now I need to create the exponential of some values, and I need to calculate the root values. So let's just Rust sqrt, let's check that. Maybe it's implemented. I guess I found that out already, that this kind of implemented on the types itself, which made sense. It was the same with the apps function, I remember. So maybe there is an square root function there. Okay, there is a square root function there. So is there some sort of pow function, maybe? Powi? Oh, of course, for floating point and for integers. Yeah, that makes sense. Returns a new number and does not mutate the original value. Yeah, that's what I would expect, actually. Okay, so that's how we do this. So that actually is, I actually kind of like that. So what we are doing here now is we are returning self.x.powi2 plus self.y powi2 plus self.z powi2 plus self.w powi2, and we want the square root of that. Yeah, I kind of like that, I guess. Magnitude. And we need to define this one public so that it can be used on the outside. By the way, if you are asking yourself now, why the hell is he doing this with 4 values? Actually, the theorem of Pythagoras works in n-dimensional spaces, essentially. So you can do this with a dimension of n, and we are simply doing it with n equals 4. So we are doing this in a 4-dimensional space to get all our tuple components into there. Even though this is either 1 or it is 0. But essentially, if we are doing this to a point, we shouldn't do this on a point, because the magnitude of a point doesn't make sense. But it's a hint from the book to calculate it this way in order to maybe find out bugs later on if we are essentially using a point where we should have used a vector. And nevertheless, we can actually calculate the magnitude of a 23 component or 23 dimensional vector if we would like. Doesn't make sense in our case here, but we could do it, so why not implement it? So it seems to work that I have now this different implementation sections. So let's check if now this is working. That's great. I like that. So now I will simply add a comment here which says tuple type related functions, I guess. I like that. And here I will add tuple operations. Come on. Or tuple math operations. that's nice. I like it to have it split up this way, so I can actually have this in different sections of the file. Yeah, that's quite nice. So what's the next thing here? Do we have a lot more tests regarding the magnitude? Yeah. So let's create those tests. What are different other tests? Computing the magnitude of vector 0, 0, 1 and computing the magnitude of vector 0, 1, 0. Okay, I guess it makes sense to have a specific tests for those. And by the way, if we would be implementing this in a real test-driven way, which we are actually not in a strict manner speaking, we would only have satisfied this first test now with our implementation by, you guessed it, just returning the value 1, because it would have satisfied this, but not the next tests, and then going on and iterating on all those test cases and refactoring and changing the code until it matches all of them. But as this is quite simple here yet, I guess we can quickly implement this. Oh no, what have I done there? That wasn't right. So we can it this way. So let me concentrate on what I'm doing here, because it's not that simple. So now we have magnitude of vector 0, 1, 0 and magnitude of vector 0, 0, 1. And this should still pass. All tests are passing. Nice. What is the next test? It's the magnitude of vector 1, 2, 3. And this is now getting into some more interesting result values, I guess. Vector 1, 2, 3. Actually, I'm starting to ask myself if there are... I think I will Google this next once we have finished it, if there are data providers for tests in Rust, because all this data we are putting in here formally cries out data provider. So there's one more, 1, 2, 3, and we will have minus 1, minus 2. Okay, I don't vector. Let's do it this way, because I don't know. Or let's off negative vector 1, 2, 3. So yeah, let's do this one. 1, 2, 3, and minus 1, minus 2, minus 3, and the magnitude of this should be the square root of 14. So let's do this dot square root, but actually I want it to be written like this, because this should actually be the same, because the length of those two should be identical. But now what is this? Can't call method sqrt on ambiguous numeric type float. Interesting. There seems to be okay. Interesting. Can I kind of typecast this one in an F? Is it like this expected value, build-in time, not a value? Okay, let's check how we typecast. Typecast Rust. Casting Rust example casting. Decimal. Yeah, I guess. What? Rust provides no implicit type conversion between primitive types. Yeah, that's okay. That's actually perfect. I like it. But explicitly type conversion can be performed using the as keyword. So if we do like as F64, it should work. Yeah, okay. So now we are talking. So they have some sort of ubiquitous type float, which then most likely can be transferred over into a float 32 or float 64 or something like that, which all of those are, and then are transferred by the compiler into the correct representation by what it needs at this point. I'm not sure. So yeah, let's check. works. That's nice. So, but now let's take a look at if there are something, just a quick look, is the Rust test data provider. Is there something like this? How can I create parameterized tests in Rust? Is there any chance to do that? Java, yeah, it's like a parameter. Okay, so the built-in test framework does not support this. The most common approach used to generate a test for each case using macros, like what the hell is that? Rust uses, nice. Rust seems to use those what are they called again? Those Lisp style macros, which are really nice to use. I didn't even know that. Yeah, so I guess I would have need to read up on the syntax of this, or I could just copy this stuff here. Okay, maybe not worth it yet. Maybe I will refactor stuff at some point. So I think we will now stay with the where is my Visual Studio Code? There it is. With the kind of stuff we are doing now, like defining all this by ourselves. It's not that bad. So as I said, maybe I will refactor it in the future, but we will see. Okay, the next thing is that the book is explaining what a unit vector is. A unit vector essentially is a vector with the length 1. You may recall it from your math class, but it's quite interesting to have unit vectors, because then you can compare vectors. Like you can easily determine the angle between them, and you can easily determine if a vector is just the opposite direction of another one and stuff like that. So the problem is not every vector has the size, the length 1, so the magnitude 1. So what we are going to do there is to normalize a vector. Normalizing simply means we are going to take its magnitude and we are dividing the vector by the magnitude. And there it happens now. We have a vector pointing into the exact same direction, but with a length of 1. So do we have tests for normalization here? Of course we have. Nice. So let's take a look. Normalizing vector 4, 0, 0 gives 1, 0, 0. Okay, that's kind of not really a test name I would want to use here, but maybe we can write it in a slightly other form. So fn normalizing vector, what is it called? 4, 0, 0. This should actually be kind of okay. So it is, yeah. So let's implement this one. We have a let v is a tuple, which is a vector, which is 4. Can I actually, okay, I see. I can tap through this. 4, 0, 0. Kind of strange syntax completion for that, what the IDE is doing there. So now we have this vector v, and now we want our let expected result. Yeah, our expected result is a vector again. And this vector actually is 1.0, 1.0, 0.0, 0.0. No, there's somewhere there. And we have actual result, that is v dot normalize. And then we have assert equality, from expected, no, actual result, expected result. That's the direction we are doing it here. So, okay, so of course this will not compile. No, because the method is not found. So let's implement it. Should be should actually be quite easy. Where is it? Where's our math? There it is. So we have a function now called normalize. And this function just gets the, come on, reference to self, and it will return self. Yeah, it will return another tuple. Yeah, okay, so that's nice. Come on, self divided by self magnitude. Cannot divide tuple by f64. Why not? Okay, cannot divide ampersand tuple by f64. Is there any way to kind of dereference it? So yeah, I guess let's check if this compiles, and yeah, it works. So nice. That's nice. I really like this. As we've already implemented scalar division and we have this magnitude, we don't need to do it again on all those. Yeah, I like it. I really, really like it. So let's test fn. What's the next we are checking here? Normalizing vector 1, 2, 3. Of course, we are normalizing vector 1, 2, 3. Normalizing vector 1, 2, 3. So why not? More or less, this is the same. Let's do this. So we have the vector 1, 2, 3. And we are expecting, yeah, what actually are we expecting there? That is hell of a output there, I guess. Yeah. So are we doing it this? Let's try it like it's 0.26726. But I guess it's just an approximation. 1.53452. Maybe our floating point precision will bite us here. I actually kind of hope it will bite us here, because I'm eager to implement something else in Rust. Okay, it failed. Why did it fail? Most likely because, exactly, those values are not precise enough. Okay, first of all, let's make a note here. This is 1.0 divided by the square root of 14. And this is 2.0 divided by the square root of 14. And this is 3.0 divided by the square root of 14. Because the length of this vector is 14. You can easily sum it up by 1 squared, 2 squared, 3 squared. It's 14, and the square root of that is then the length, and so we are dividing by this one. So these are only approximated values, and they are in the book for a reason, because they are given here explicitly as something to test against. It's to ensure we have, I guess it's to ensure, it's not written here, but I guess it's to ensure that we have implemented our fuzzy matching against floating points. Because we essentially have implemented it here somewhere. We have said, okay, let's let's make sure that we are comparing them and they are the same by a certain precision. Not only because we don't want always to have such big numbers there, such big decimal numbers, but because floating points can differ in certain operations, and there can be we actually have, as we only have a certain amount of space to store each floating point number, we can't store floating point numbers in an arbitrarily precise way. So if we are doing math with them, which we are going to do later on, a lot more complex math and operations which are intertwined and stuff like that, we are getting an error there. The calculations will always produce an error, but we want to make sure that in the end there is a result which is close enough to what we expect. And as I have seen this, it's actually the way why we can actually do this here. Where is it? Like assert equals with not with these values, but with our whole tuples, is because I've added this here, this derive, and especially this partial equality thingy. Because that is a trait for equality comparisons, which are partial equivalence relations. So yeah, this trait allows for partial equality for types that do not have a full equivalence relation, for example in floating point numbers. So floating point types implement partial equality but not equality. So that's actually the way, because we can have something like not a number, which is a valid floating point, but but not a number is not the same as not a number, because that's not the same value. It's the same with infinity, I guess. I don't know if Rust has a construct for that, but they have a construct for not a number. They most likely have one for infinity, and infinity doesn't equal infinity as well. So, but we can actually implement this trait to implement how this equality is calculated, or this partial equality. And so as far as I get it, we simply implement this one here, and we can then return a Boolean which says, is this partially equal or not? And by doing this derive of partial equality, I guess it's kind of automatically creating for us one which is comparing, which is essentially saying, okay, these two structs are the same, partially equal, two tuples, if the partial equality or equality of everything within it of those types, and Rust knows the partial and equality comparison function of those types, is the same as well. So, but if we now remove this here, which I'm doing, I guess most of our tests won't work anymore. No. Because the system will tell us, yeah, in our first thing, that it cannot compare those. I guess that's why I Googled and added those informations for in the first place. But now I want to actually implement this myself, so I can do this. Should be more or less the same comparison. So let's implement this ourselves. Let's implement what is it? Partial equality for tuple. And I guess we only need to implement EQ then, and this is other, which is it actually, do I need this one? Maybe I need this one? Yeah. No, this is self, and this is self then as well, and it should output a Boolean, not a book. And now, but not the implement, wait a second, what? Has self, oh, of course, self, no, the first one doesn't need, oh, okay, But now we are getting only, we are not, yeah, okay. So, incompatible type for trait expected and tuple found struct tuple. Okay, so it's working on references then, which kind of makes sense. So, okay, let's return something here, and let's return actually. Now, cell, no, how did we call this function? We have it already implemented, which does this, it's f64 fuzzy equality, and we want to I want to implement this one here. So let's f64 fuzzy equality, let's do self.x, no, other.x. So it's this. And they all need to equal in order for this whole thing to equal. So let's say and f64 fuzzy equality, same thing for fy, other y, f64 fuzzy equality. I really don't like this strange snippet-like completion of this methods. I really don't, but maybe I have to live with that, because that's simply not the way I'm implementing it. Other y and f64 fuzzy equality self.w other.w. Okay, now it's telling us that this is an unnecessary parenthesis, and I get it, but okay. If it's formatting it like this, I will remove this parenthesis. Maybe like this. Yeah, in this case, I like it better with a explicit return. And will it cry if I do this? Okay. It's just an optical thing. But now it should actually, let's run the tests, should able to run our tests again. 12 passed, 10 failed. Kind of, what the hell? Okay, so assertion failed. Left is not right. That's... What? Okay, I obviously did something wrong here. What did I do? What did I do wrong? Of course, they didn't all fail. 12 passed, 10 fail. Oh, one should do other z here. Okay, let's try again. Okay, now they passed, including this one. So as we are now, because these values are precise enough for the test, and now for this fuzzy test with a given epsilon. So now this should work actually. I'm not 100% sure if we should have just implemented, but that's far beyond my capabilities yet. Another macro like assert fuzzy equality, which then uses another trait instead of the partial equality, our own trait, our fuzzy equality trait somehow. I guess that would have been a lot better, but that's... Let's just mark it here as an idea. Maybe implement own fuzzy EQ trait or fuzzy partial EQ trait in the future, combined with assert fuzzy EQ macro. Would be a lot nicer. Okay, so now we have that. So now normalizing this vector 1, 2, 3 works as well. So what is our next test? The magnitude of a normalized vector is 1. Yeah. Ah, okay. Yeah, makes sense to kind of check that. So not only that our math is right, but that our assumptions are actually right. So we are checking now that the magnitude of a normalized vector is 1. So we have this one here, and the expected result is 1.0, and the actual result is normalized dot magnitude. And we are assuming this can go somewhere else, and we are assuming this is the same, and it should be, yeah. Because once we've normalized a vector, that's exactly why we are doing it. We want that it has a magnitude of 1. So what is actually the next thing we are implementing here? The next thing is the dot product. And then comes the cross product, and then we are going to use all that stuff to do some work with it. I would have just I was thinking about saying, but yeah, that's then we are using it in a very, very easy way and a very simple way to use it. We can't really do a lot of this with it yet, but yeah. As it is already kind of getting a little bit later here, and it's almost time for dinner, I guess I will make another break here in this session. We have now implemented quite a lot of stuff. We have learned a lot of stuff, but as I have promised, it has gone a lot faster than before when I just needed to figure out how to get started with all this in Rust. And there will be a lot of slow segments again as well while I'm figuring out other stuff. But as I told you, we will figure this out together, and we will go along here. And yeah, I guess this is it for the second video implementing chapter 1 of James Buck's The Ray Tracer Challenge. There it is. And yeah, I think we made a lot of progress there. Yeah, I've said I will put it up on GitHub. The link will then be down in the video description, of course, after I've put it all together and uploaded it. Yeah, so thanks for watching, and I will see you in the next part of this series, where we will go ahead and implement, I guess, the rest of chapter 1, and maybe even get started on chapter 2. We will see. So thanks for watching. Have a nice day, evening, whatever it is. Speaking of time of day, where you are currently at when you are watching this, and goodbye. See you next time.